We're going to finish talking about dynamic programming today. There are at least 2 more problems on the syllabus in dynamic programming. I don't know if I'll get to both, but I'll certainly get to this one, the knapsack one. The other one is a problem called the bandwidth minimization problem, which is a really cool problem that I worked on myself about 15 or 18 years ago, and it's got a lot of neat applications. And if I get to it, I get to it, and if I don't, I don't. But I do want to make a transition between dynamic programming and greedy algorithms, and then head over toward greedy algorithms. Okay, so this problem is kind of famous. It's interesting that our book doesn't have a section on it. They just throw it in the exercises, and that's always an author's choice when they have a big book, what they're going to actually throw a section in and what they're going to throw in the exercises. So this isn't in the book, and you should listen carefully, because there's a problem on this in the problem set, a variation of this, which is one of the earliest NP-complete problems. This is an NP-complete problem, and the variation that's NP-complete is the problem of if somebody just gives you a whole bunch of numbers, can you split them into 2 sets to make the sum of the 2 sets equal? Like the electoral college problem that I gave you guys. Can you take all those numbers, split them into 2 parts, and make them equal? That's an NP-complete problem. It turns out, though, that if the numbers are very small, then you can solve it in polynomial time. So it's a problem whose size of the input is the number of different values you're giving it, and there's another aspect to the size of the input, which is the actual magnitude of the numbers themselves. So if you call the number of numbers n, and the size of the largest one, say capital M, then there's an algorithm for both these problems, but the partition problem in particular, that runs in the number of different numbers you have given to you times the magnitude of the largest one. That looks like a polynomial time algorithm, except for the fact that the largest one can be very big in terms of the number of numbers you have. This can be 2 to the n, it could be 2 to the 2 to the n, it could be indefinitely large. What's more, you would never think of this, and Rob asked about this last week, you don't think about this as a polynomial algorithm, even though it looks linear, because this m is the largest number we have, but the size of that number is the number of bits in that number, is how you represent it. So if I put in the number 1,000,000, the m would be 1,000,000, but the size of the input would just be the log of 1,000,000. And in terms of that size, this capital M is exponential. So it would be, if you call the size s, this is really 2 to the s. Now we normally don't write order n 2 to the s, where s is the size of the largest number, because it's just kind of a funny way to write it. But that's the way we really think of it. It's an exponential algorithm in the size, in the number of bits and the actual input of the largest number, times the number of different numbers. So it is an exponential algorithm. The problem is NP-complete. If the numbers are very small, if this s is teeny, if this m is very teeny, if they're constant, you can definitely do it in polynomial time. So problems like this, that have algorithms like this, are called problems that are solved in pseudo-polynomial time. It's not really polynomial time, but if you can get this other parameter down low enough, then it is polynomial time. If the largest number was, say, at most the square of the number of numbers, then it would be an order n cubed algorithm, n times n squared. So these are called pseudo-polynomial time algorithms. They're useful. They're one of the many techniques of dealing with NP-completeness. You never give up on an NP-complete problem. You just try a little harder. Sometimes you do engineering tricks to just try to get a little bigger and bigger instances that work. And sometimes you come up with solutions like this, which will work in special cases. Other methods are doing approximation algorithms, where you give up on getting the right answer, but you come up with a very fast algorithm that gives you an answer within 10% of the right answer. Sometimes you come up with probabilistic algorithms, algorithms that are guaranteed to give you the right answer, but only 90% of the time, and say 10% of the time they just give you a bunch of crap. So different strategies, and lots of different strategies for NP-complete problems. The most common strategy is look at special cases and see if the problem gets easier. And that's what we're really doing here. Looking at the case for small size numbers, this problem is doable. For large numbers, it's hard. Well, what is this problem? It's a generalization of that electoral college partition problem. And the best way for me to describe it is with a little bit of a Raiders of the Lost Ark style story. Okay? Picture that you are no longer good people working hard this year trying to get through ADU. You are robbers, highwaymen, looters, bad guys. And you walk into Jeff Radcliffe's home, and Jeff Radcliffe is a clever man, and he knew you were coming. So he left a little room, which is suspicious, because normally when you come into a house, there's nothing there and you ransack the place. But today, there's a big sign that says, "Welcome looters." "Hello robbers," and there are 3 boxes. No children in the boxes, just little signs. Box numbered 1, 2, and 3. And it's not the Monty Hall puzzle. It's just Jeff's sense of humor here. And in this box, it says, this box has items that have size 2 and value 5. So if you take out items from here, say they are 2 cubic feet, whatever, and they're $5 each. And he was careful to sort through all his belongings to put it into one of these boxes. So it's just his way. Here's another box. Size 3, value 8, and another box, size 5, value 14. Good stuff in this box, but it's bigger. In the knapsack problem, big things come in big packages, not small packages. Smaller things usually are worth less. Not necessarily, but makes sense. So you come in, and you got a knapsack with you, hence the name of the problem. Here's your knapsack. It's a knapsack. It's a knapsack. It's got 49 cubic feet in it. You got a certain amount of size in your knapsack. That's a lot of feet. All right.
Did you bring Seth along to carry it?
I brought Seth along to carry it. Your goal is to fill your knapsack up with as much loot as you can. Okay, so you want to get the most money out of this. You want to get your most value for your thievery. The thing is, Jeff has set up his home so that if you actually walk back out of the house without the maximum amount of value that you could possibly have retrieved from his 3 boxes, then the rug will give way, the place will cave in, you'll try to roll out, and you'll be destroyed. But if you have the actual maximum, if you get the Holy Grail and solve this problem, then he feels, well, if you studied algorithms hard enough, then it's okay for you to rob me. And there we go. Now you're all motivated. At least Jeff is. How do we figure out how much stuff to put in the knapsack? Here's the thing. Let's do a greedy strategy. Let's be really greedy. Let's just do things because we've been taken aback and surprised by this problem, and we haven't thought about it much, and we're on the spot, and we think somebody's going to come home soon. So how would you do it? You're on the spot. That means nothing clever allowed. Just you got about 3 minutes before you think the cops have set you up here. So what do? The most valuable thing. Okay. The thing is that there's a trade-off between value and size, but let's go for that. If we pick the most valuable thing, that's a nice greedy strategy, and we'll take as many of that as we can. Let's see how much we get. How many of these sizes can we fit in our knapsack? 9, right? That's 45. 9 times 5 is 45. Our knapsack holds 49. So we'll get 9 of these things that are valued at $14 each. We still got room left in our knapsack, so should we go for the next most valuable thing?
But if we're doing the greedy strategy, yes.
Well, if we did the greedy strategy, we go for our next most thing, and that would give us a value of 8, and that would leave the knapsack with 1 cubic foot empty that we couldn't fill up anymore. But everybody's looking at it, and they think, okay, well, once Michael's picked 9 of these 14 objects, we've got how much room left? 4 left, so maybe we should take 2 of these. That gives you $10 worth. Just fits to the top instead of 1 of these, which just gives you $8 worth. So already, taking this as a first guess, you should be hit with the fact that, oh boy, now that I noticed this second part of putting 2 two-size objects in instead of 1 3-size object, I have a little doubt about what I did at the beginning. Or you should have a little doubt. Because if this strategy was going to work all the way through, it should have worked for the last cases too. Now maybe that happens to be the max and you'll be saved, and maybe it isn't. But if you know they're going to be out of the house for a couple hours, you can learn how to solve this problem and be sure. All right. Any other ideas besides this idea? There's another idea I think that should come to mind, very similar to this first try, and that is to not just to take the most valuable, but to take the most valuable per cubic foot. Okay, so this is, I think it might be the same in this case, but at least that way you're getting the most per size. And maybe that greedy strategy is consistent or works. Well, let's try it. What is this one per cubic foot? It's 2.5, and this one is 2.66666, and this one is 2.8. So it looks like, coincidentally, we actually did that. And maybe that's even what you meant at the beginning. No, but it's OK if you didn't. Picking the most value is one. Picking the best value per size is the other. I'll tell you right now that none of these strategies work. For one thing, this best value per size would give us the same exact thing we just did. And that didn't give us the best maximum. Right? It gave us 9 of these objects, which was how much value? 9 times 14. Plus, let's go ahead and finish the greedy algorithm. We'll fill up this, because this is the next best value per size. And we get how many of these in there? We can fit 1 in there, so we get another 8. And that ends up being 26, 134. OK. You walk out the door with $134 worth in your knapsack, and you're going to die. Okay, that's not the best. There's a better way. So how do we solve this problem? This problem has a beautiful recursive structure that's really reminiscent of that theorem that we've done a number of times, this one. If you remember the proof of this theorem, you fix yourself on one object, and either you include it or you don't include it. And one case is where you include it, and one is when you don't include it. And the number of different counting adds up the same. It's the same kind of idea here, and it's an idea that recurs a lot in these dynamic programming problems, in the recursive structure. So it's a good thing to focus on. I'll try to, here's the knapsack. It's 49. Let's talk about how to really solve this problem over here on the right side. OK, other questions so far? One little correction that I'm going to make today as I was reading through my notes this morning. In the actual formula I write in my notes, I calculate the 2 possibilities. One when you include it and one when you don't include it, like I'm just going to explain in a minute. And then you're supposed to take the one that's the biggest. But in my notes I write min instead of max. So it should be max. I'll change it. But don't think there's some clever thing going on there. It's just a typo. How do we solve this problem? Let's start with the following notation. This notation means C stands for cost, or what's the best money I can get. C of 49.3 means what's the best cost I can get in a knapsack of 49 when I'm choosing from all 3 boxes. One possibility is that we include things that are in the 3rd box. And one possibility is that we don't take anything from the 3rd box. Okay? 2 choices. Fix yourself on one box. Usually we fix the last box because it makes the notation easier, you'll see in a minute. Fix yourself on the last box. Either you include stuff from this box or you don't. Let's say you don't. You don't take anything from this box. It's out of the picture. Then what is the best you can do in terms of cost in using this notation? C, 49. You still got a knapsack of 49 because you haven't put a thing in the knapsack. But now you're only choosing from the first 2 boxes. That's one possibility. What's the other possibility? Is that you pick something from this box. Well, imagine that we're picking one thing at a time. So if you pick one thing from this box, what happens? Your size of your knapsack goes down by 5, and your value goes up by 14. So the best you can do is C of 44. You can still pick from the 3rd box again, so we're leaving that 3. But there's an additional amount that you gained by doing this, and that was the 14. These are the two choices. Take the maximum of these. Whichever one is bigger is the answer. There's only two ways to do it. Either you pick something from the third box or you don't. And if you pick something from the third box, then you get a value of 14, a knapsack of size 44, and you can keep picking from all three boxes. If you don't pick anything from the third box, then you've got a knapsack of size 49 still, and you've only got two boxes to choose from. You can write this up in general, where this is the value of the third box, and this is the capacity of the knapsack minus the size of the third box. You can make it in general, but it's perfectly clear, I think, using this example. OK, are there questions so far?
How does that handle that the box is infinitely deep? We can take as many items as we want.
The fact that we left the 3 there. And you're right, Todd, that if we change the rules here, where say there was a limited number, we would have to have that somehow integrated with how this number changed. But in this case, we leave that number 3. That means we can take it again and again and again. This choice implies that we're not taking any, so it's OK to cut the number down. It's a good question. Are there other questions about this idea? If you get this idea, you're 95% of the way. The rest of this is just going to be implementation, discussion of how long it takes. This is the idea. We've got to work out the details now, but that's it. The knapsack problem is naturally recursive. It's defined in terms of itself. So there's lots of issues now, but before I get to them, I want to answer questions. Make sure we're all in the same spot. Are there questions about any of this so far? Donna, good? No question? No? You're looking thoughtful. OK. No, no. I want that. I want those neurons firing.
You wrote it picking from the third box. You could do it with the second box or the first box.
Say that again, Neil?
You wrote it writing picking from the third box with the side.
I focused on the third box.
You could have written it.
I could have written it the other way, but then it would go against what I mean by this notation. What I mean by this notation is you have a knapsack of 49. You can choose from any of the boxes starting at 1 up to this. So when I do the recursion, I just work my way back from the larger numbered boxes. So this 2 means I can pick from boxes 1 or 2. And a 3 means boxes 1, 2, or 3. But certainly I could define it the other way, and then I just have funnier looking notation here.
But you want the largest one on singled out? Is that part of the?
No, I could do it the other way. No, there's no reason. There's no reason other than notation that I did it that way. I could number these the other way, and it would work just the same. Absolutely. Other questions? OK. Well, what makes a recursive problem not turn into an infinite loop? Some kind of a base case. It bottoms out. Is this going to bottom out? In this example, the right parameter goes down. So that's good. But in this example, it doesn't. The left part goes down. The good part is that at least one side goes down. But that means we're going to need a base case that's going to handle if the right side gets low enough, we do this. If the left side gets low enough, we do that. We cannot just have a base case for one of these parameters, because then the other one could conceivably get lower and lower and lower. That one could stay the same, and we would never end. Okay, so we need a base case for both sides. So what should the base case be? This isn't tricky. It's just some details that we have to take care of. What should C of 8, 0 be? Sooner or later, we're going to get down to that. What does that mean? I got a knapsack of size 8. I'm taking from no boxes.
So that's never going to increase your value anymore.
So what's the most I could get?
0.
I get 0. Right. So if I'm not allowed to take any of the boxes, if this number comes down to a vacuous 0, that means I can't take from either 1 or 2 or 3, then the best value I could come up with is 0. Tony?
When would that happen?
Let's see. Let's do C of 7, better yet, 5, 1. Let's do C of 5, 1 according to our recursive relationship. You know what? Let's first do C of 5, 1 in our heads. I got a knapsack of size 5. I can only take stuff from box 1. What's the most I can do?
10.
I can fill it with 2 of these objects. Give me a value of 10. That's what C of 5, 1 is. You can do that in your head. I could have made that the base case, but there's some calculation that we have to do. So let's just run it through the recursion and see what happens, and then you'll see where that other base case shows up. What happens if I run this through the recursion? Either I use this box or I don't use this box. If I don't use this box, then I end up with C of 5, 0. That's where the 0 comes in. And if I do use the box, what do I get? C of 3, 1 plus 5. I got to take the bigger of these two. Now I have to know that this one is worth nothing. That if I'm not going to use the box at all, I get 0. So that this one will never be chosen as the maximum. So C of 5, 0 should be a base case, and it stops me. So C of 5, 1 turns into C of 3, 1 plus 5. That won't happen. That won't ever be the max. And C of 3, 1 turns into C of 3, 0. C of 1, 1 plus, well, plus 5. So the maximum of these two is going to be the bottom one. C of 1, 1, if you do that one more time, and we'll do it one more time, you'll see what happens. But right now our maximum is 5 plus 5. We still have to calculate C of 1, 1. So what Tony said is true. C of anything comma 0 is 0. It means you're not allowed to use anything from any of the boxes. You can't get any value.
You get lots of end cases like this, and you end up backing out.
You mean if you really do this recursively, you get a horrible duplication?
Well, yeah.
Yeah. Let's do C of 1, 1. According to the same recursive idea. These are the details I wanted to do. So we're not off on a tangent. If you're thinking, oh, I'll wait till he gets back. We're on the main stream here, so stay with me. C1, 1. Two possibilities. What are they? C of 1, 0. That means that I am not using the first box, or I do use the first box. What happens then? It does work.
No, you can't take any from knapsack. The knapsack's not big enough for the value.
Well, we can still subtract the size from the capacity of the knapsack. What's the size of an object here? It's 2. What, you can't take away 2 from 1?
Not when you're talking about knapsacks.
I owe you some space in my knapsack. It's okay. I get negative 1, 1. Chris is right. It doesn't make any sense to take things away from a knapsack and turn them negative. But if we follow this recursive thing through, that's going to happen. And that's our base case. That means, hey, quit it. Don't do it again, because you're just going to get a more bigger negative knapsack, and you're not going to get any richer. So what is C of negative 1, 1? When that first number turns negative, it means you got no room. You're not going to get any values. I don't care how many boxes you can pick from. So when this number is 0 or negative,
When it's 0, it should be okay. Yeah. Means we filled it up entirely.
Well, but it would
no,
still
but
be zero
what's the
value.
best capacity you can get in a knapsack that's completely full?
0.
If I said 0, 3, you walk into his apartment, and you brought in a knapsack that was filled with groceries.
Okay.
And you put your knapsack down, and you say, dough. Right? And you'll walk out. C03 is 0. You can't get one more thing in that knapsack. And C of negative means you brought in your knapsack and it's overstocked. You actually are looking for a knapsack to take some of those groceries out. So here are the base cases. Either the right-hand number turns to 0. It will never go below 0, because that goes down 1 at a time. But the left-hand number can skip because of the size, and it goes right over 0 into negative land. If you check for a base case here of 0, you're going to have an infinite loop. So the base case here has to be 0 or negative. And in that case, the answer is 0. So the best value you can get when the number of boxes you're choosing from is 0, the best value you can get is 0. And when the first parameter, the size of the backpack, becomes negative, the best value you can get is 0. Otherwise, you can always use this recursion. Those are our base cases. Yeah?
In that formulation, wouldn't it be C of negative 1, 1 plus 5?
Right.
Oh, yes, it would be.
In which case, wouldn't it be 0 plus 5? So you would see that as...
It would be it would be 1 plus the value of this. So it would be c minus 1, 6. You're right, it would be a 6. I was careless. No? You're wrong. No, we're adding to this one, right?
The way you word it, you're adding a plus at the end of the value.
Oh, jeez. Oh, because the 6 is here. Oh. Sorry.
I'm just concerned if we're taking the max of this.
Yeah. You're going to get a 5 now. It's no good. Yeah. You're 100% right, Kevin. I'm a little bit careless. You're right. I don't mean that this should just be 0. I mean that if this turns to negative,
It should just not be allowed.
it should just, the whole thing's 0, right? You don't add the number down at the end, right? Right, so if this first parameter is negative, you just return a 0 right away without doing the addition. And if this one's a 0, you return a 0. You're 100% right. I was a little careless. All right, so now that we've got the base cases, I hope, down pat, let's try to figure out the answer to this problem. The C49.3. As you might guess, C49.3 depends on 49.2 and 44.3, and as you keep going here, you're going to get these overlaps. The subproblems are going to start overlapping, it's going to be a mess, and how long is it going to take us to get it? It takes a lot of steps. What happens here is that it's hard to analyze this recurrence equation precisely, but in the worst case, you have 2 subproblems, each of which might go down by only size 1 each time. This always goes down by 1, and if these sizes are small, then they go down by 1. Okay, so that's t of n equal t of n minus 1 plus t of n minus 1, and that's like towers of Hanoi. That's exponential. So you don't want to do it this way. You want to do it in a bottom-up way, because if you do it in a bottom-up way, what's the maximum number of subproblems you could possibly have if you make sure you do each one once? This number ranges from 1 to 3, or in general, this number ranges from 1 to n. And this number ranges from 1 to capital M, to our biggest number that we have, or to the size of the knapsack. So if your size of your knapsack is 49, call that M, then this number ranges up to capital M. And if this number of objects you have is little n, then this algorithm can be done. This is only a maximum calculation, so every step is constant time. It can be done in capital M times small n. And that's, what's that?
Starting at the bottom.
Starting at the bottom. If you start with the base cases and work your way up to 49.3. Okay, questions?
You can't use this divide and conquer on this and to have 2 little knapsacks and fill them up recursively? Doesn't work.
Yeah, because they would turn into 2 other little knapsacks, and yeah, you'd have a multitude of knapsacks. Yeah, as many knapsacks as there are the stars. Look and see if you can count them. It'd be a religious experience right before the trapdoor closed on us and prevented us from leaving with our loot. Let's actually do a calculation here and see if we can figure out what the best value for C49.3 is. We have a class, so we can do this in parallel. Well, almost in parallel in the sense that you do need the previous values to give you the next values. A lot of this we can short circuit. Instead of going out of the base case, we can just eyeball something and see. So let's try to do that if we can. 1, 2, 3. And these numbers are going to range 1 all the way up to 49.
Just missed the number, Sean. 1, 2, 3, 4, 5.
10.
No, there's a 6 missing. 5, 6.
No, I got a 6 there.
No,
Ah! 6 isn't coming this year.
Try, you said 9.
10, 20, 30. I'm going to need a little more room. We'll do this for a little while, and after that you'll decide there's a reason you have computers do this. Maybe you already think so. 10, 20, 30, 40. What did I miss this time? All right. Let's see if we can do this fast. Ugh. Here are the values again. Size 2, size 3, size 5, value 14, value 8, and value 5. Size, value. Okay. This is only using box 1. So we can almost fill this whole row in, eyeballing it. This is the knapsack size. If I have a knapsack of size 1, and I'm trying to fit in things only in box number 1, box number 1, 2, 3, only in box number 1, I can't fit anything in there. So that's 0. If I allow size 2, I can fit one thing in there. So that's 5. Size 3, it's still 5. Size 4, I can get 10. 5, still 10, 6, 15. Every time I move up 2 sizes, I can get another object in there. And I'm only counting things from box 1 here. So this is going to go 10, 15, 20, 30, 35, blah, blah, blah. You can figure out what's... All right. Let's do this one. You ready to quit? You want to know what the best you can do with CF 49.3 is?
Sure.
You think I know? It's better than 134.
Is it better than 136?
It's 136. Well, now we don't have to do this. Let's do an example a little more until everybody makes sure they gets it. Let's skip over to second row. We can always fill in the first row as we need it because you guys are fast. So 2, 1. You can pick things from 2 boxes now, but you only have a knapsack of size 1. 0. 2, 2. CF 2, 2. It's the maximum of... No, but here we can take either from box 1 or 2. This isn't just box 2. This is anything through box 2. So CF22 is going to be CF21, right? That means we're not taking from box 2. That's the best we can do with just box 1. Or we do take from box 2, which is, we have a size of 2 here. We take away the size of box 2's object, which is 3. That gives us a negative. We don't include that. So it's just going to be CF21. CF21 is 5, so CF22 is 5. Okay, that's the best one. Every one of these entries is going to depend on looking up 2 other entries, doing an arithmetic, and calculating a maximum. It's going to take 3 or 4 steps. Constant time every time. So we're just going to fill this table in. If we were machines, we'd fill it in fast because it would take us, 2 microseconds a shot. But we're not machines, so it'll take us a little bit longer. Let's go over to C23. Okay, what does C23 depend on? Kevin, you want to tell me what it depends on? You're looking confident.
Sure. Depend on C22.
Okay, why?
That would be we didn't take anything at all from box 3.
Good. If you don't take anything from box 3, that means you can do the best you can with a capacity of 2 and a box choice of 1 or 2. Or
It's going to be C of... If we did take one of 3, that's size of 5, so it'd be C of negative 3.
right, so it's already excellent. So if you take one of object 3, it's actually too big to fit in your knapsack, so that gives you nothing. So you get 0 for that. So the maximum of 0 in this has got to be C of 2, and C of 2 is 5. So that means C of 3 is also...
No, that was the right spot. If you were wanting
C of 3 is 5, right? All right, we could work our way all the way across to C49, and it would take us a long time. And at this point, I don't think we'd gain anything from it. So let's stop. But the way the algorithm would work is it would go this way first. How come? Why does it go this way all the way across first? What order? Remember, the order that you fill the table in is important because you got to make sure that you do the sub-problems that depend on the later problems first. So what does every problem depend on? It depends on the one that is directly above it, because you take one away from the second parameter, one box less. And what else does it depend on? It depends on something in the same row, but further to the left, because you're taking away part of the knapsack. So as long as you go from the top to the right, top down, left, right, you will fill in all the ones that are above and to the left before you get to the ones that show up. So if you're here, this will depend on this and something back here. As long as you go this way, you will fill this one and this one up before you get to this one. And that's why we go left to right down in this order.
So you could go top to bottom, then left to right? The order is
If we did this way, that's okay. That's okay too.
counterintuitive.
Yes, a little counterintuitive, but okay. Perfectly fine. Perfectly fine. All right, so we talked about the complexity, we talked about the base case, we talked about the recursive relationship. There's not much left to talk about, except that this is a really cool problem, and it's a kind of problem that does allow for lots of engineering tweaks. One thing that I once did that was pretty successful, I didn't do it because I've already thrown you guys too many problem set problems, but one really cool thing is to make a competition in class where everybody's supposed to write up any algorithm they want for this problem. There usually end up being variations of this one. And the idea is to see who can solve the largest size problem before the time period of the competition is over. Kind of like when you all try to get the highest score in asteroids before 5 p.m. So this is the largest knapsack problem. So I gave like 20 knapsack problem sizes, and you have to solve them all. But as you get to the end of the list, they get very huge, to the point where any typical try at the very huge ones will take, 100 years. And you need to come up with all sorts of techniques of trying to get the right answer, including techniques that might actually not guarantee to get the right answer, but are maybe approximation or probabilistic. Any idea you can. Engineering tweaks. So it's a cool competition, but we won't do it. It's very time intensive. Once you get the thing running, you can tweak it forever. Okay.
How fast is this again?
What's that?
How fast is this one?
This takes time proportional the number of boxes times the size of the knapsack. And that's similar to the special case of this problem, where it's the number of different values in the electoral college times the size of the largest value. That would be the number of the different numbers. That would be the size of the largest number. This is the most general version.
You can do it like with brute force and try every possibility.
Oh, sure.
Is that NQ?
What do you think? What's every possibility? You mean every possibility as far as how many different things to pick from these boxes? So how many different ways are there to pick things from these boxes? Well, it's unlimited choice from each box, and there's n boxes. So does n to the n sound right? What do you guys think?
Well, you're limited by the knapsack.
You're limited by the knapsack. So let's say the sizes, worst case, were 1. So you've got this many values. It's basically you've got this many different positions, and you're going to put in numbers that can be anywhere from 1 to 3. Right? So you've got an unlimited number of positions, m positions, and you're putting numbers in that can be anywhere from, so it's going to be 3 or n, something like this,
You just have to go
to the capital M. No, it's worse. It's worse than 3 loops. I think, yeah. Well, if you're doing this, it's just filling in this table. But if you're going to look at every possibility,
You just have to have the number you're going to take from box 1, a number from box 2, a number from box 3. And they're both limited by the size of the knapsack. So you just have to find out what combination it is, and then get the maximum.
that's right. That's right, but that ends up being this big. So in this example, it's 3. Or
If you just have 3 boxes.
but it's 3 to the m, not m to the third.
N is the number of boxes?
Yeah, n's the number of boxes.
Oh, okay.
Right? Because you have m different places to put things, and you can put either the number 1, 2, or 3 there. So it's like ternary numbers.
Yeah.
So if you try to have a possibility, it gets exponential really fast. Assuming this is large. If this is very small, it doesn't get bad. But but this way it helps you avoid that. Here's a nice version of the knapsack problem that will bridge us from dynamic programming to the greedy algorithm. If I allow you to turn these objects into liquid so that you can just pour them into your knapsack, you can take fractions of objects, chop them in half, and pour them in. So Jeff says, you know, look, this is size 2. You put it in your knapsack or you don't. And what if I allow you to take fractions of that and melt them down and fill your knapsack up to the tippy top? Everyone understand the difference? So the book calls this problem 0-1 knapsack, meaning you either take it or you don't. And the other one it probably calls fractional knapsack or something. But I've seen it more often called liquid knapsack, where you can just slice them up and turn them into liquid. So if that's the problem, then this is an easy problem. If that's the problem, then you really just go ahead and figure out best cost per size and do that greedy thing we did right at the beginning. And fill that knapsack right up to the tippy top and walk right out. And that greedy idea is perfectly natural, and it works in that situation. So this problem becomes hard because it's discrete. If you make it continuous, it becomes easy. And that's true about a lot of problems. Okay, linear programming, this integer programming that you talked about in linear algebra, that's a hard problem only when it's whole values. But if you make it continuous values, then there are polynomial time algorithms for it. So that's a good thing to remember in general. Discrete often makes things harder. Okay, questions? Good. So I have some time, and I want to talk to you a teeny bit, not too much detail, but more kind of a general discussion about the last dynamic programming problem, because you won't find it in any book. It's an example of something that appears in the literature, is interesting to maybe 500 people, and then wasn't interesting enough to end up putting it in a textbook. But it's a classic example of something that comes up in real-life research. Dynamic programming tools come to bear, and you figure it out. I won't go into too many details. I'll just give you a general overview of it, and then we'll switch over to greedy algorithm. So here's the problem. It's called bandwidth minimization. I'll describe to you what the problem is, what people know about it, and then a little bit about how to do it. Then we'll switch over to greedy stuff. The bandwidth minimization problem comes about originally from a problem about laying chips out on a board from VLSI. And the idea is that you don't really want to stretch your wires too far. You want to keep them all within some distance. So, for example, let's say I have A, B, C, D, E, F. Let's say I have this particular graph, and it represents some kind of circuitry where these are components and these are wires between the components. And I want to put this on some kind of a chip and lay it out in a line where the components are all in a single line and the wires have to connect over in a group. So this is called a layout. Let's do an example of a layout. Why don't I just try an alphabetical order layout? A connects to F, A connects to E, F connects to E, B, E, C, D make a square. There's the graph written out as a linear line. The longest wire in this graph, as measured linearly, is from A to F. It's 1, 2, 3, 4, 5 units long. The idea of the bandwidth minimization problem is somebody gives you this graph as a graph data structure. You figure out the best way to lay it in a line to minimize that longest line. So give me a better layout. Just ballpark to make sure you understand the problem. What's a better way to lay this out so that I don't stretch these lines as far as I did in this very, very naive alphabetical order example? What's a better way to lay it out?
AFE, BDC.
So keep these things closer. We'll do AFE. And then what? Let's see what that turns out to be. A goes to F, F goes to E, E goes back to A. E goes to B, B goes to D. Sorry, E, B, C, D, back to E. What's the longest wire here? 2. I know that this can't be done with a bandwidth of 1. Bandwidth of 1s are things that are, you can't possibly have a cycle with a bandwidth of 1. So this is the best we can do, and we say that this graph has a bandwidth of 2. It's the minimum over the largest of the wires over all possible layouts. So it's a minimum of maximums. This is a very practical problem. It comes up not just laying things out in a straight line. You might want to lay things out on a grid. You might want to lay things out in a hypercube. You might want to lay things out on any kind of a structure. And it doesn't just represent wires and VLSI. It also can represent processor dependencies. This depends on this depends on that, and you want to have these things be small so that they don't have to wait as long, or something of that nature. There's other measures of layouts. There's a measure that counts how many wires go through any vertical cut. So here there's 1, 2, 3, 4, 5, 6. That's called the cut width. There's a lot of things to measure about a layout, and they all represent different things in engineering. Let me tell you a little bit about this problem just to show you how hard it is. This problem, almost every problem on a graph problem, if you do it on trees, it becomes easier. Most of them become easier. The traveling salesman problem on a tree is completely trivial. Okay, there's only one path between this node and this node. So if you want to figure out the best way to get from here to here, there's only one way to do it, and you can't travel the other way. So the answer is just straightforward. A lot of problems become easier on trees. This problem is NP-complete even for binary trees. If I give you a binary tree and I ask you what's the best way to lay it out to minimize these wire things, that's even very, very hard. And people, because this is what you do, it's even hard for special kinds of binary trees. Binary trees called caterpillars, where it has one long spine and just little things coming out of the spine. So very special purpose binary trees are even hard. The proof of that is it's in a paper of 15, 20 years ago. I remember reading it for the first time. It's really gory. So you should just know the result, and you don't need to hear any of the details. However, as bad as this problem is, there's a nice result for this, a pseudo polynomial time result for this algorithm. And here's what it is. If you want to know the minimum bandwidth, that's very difficult. But say you just want to know whether a graph has bandwidth 2 or worse than 2. If that's your question, then you can solve this problem in order n squared. If you want to know the question, does it have bandwidth 3 or less, or is it worse than 3? Yes or no? Can you do better than 3 or not? Then there's an order n cubed algorithm. If you want to know, does it have bandwidth k or not, then there's an order n to the k algorithm. If you fix the size of the bandwidth you're interested in, then you can answer yes or no, does it have it or not, in n to the k.
If it had lower bandwidth than what you were checking, supposing
It would say yes.
Okay.
If it has bandwidth less than 3, you would say this n cubed algorithm could answer yes or no, it doesn't have bandwidth 3 or better. It doesn't have to be exactly 3, 3 or better. So that's a nice result. Yeah, Joe?
Is it the same algorithm that just takes longer to run, or is it separate?
It's the same exact algorithm that just takes longer to run depending on how big the actual k is. Now, how long would this run for a general problem? For a general problem, what is the bandwidth limited by? What's the worst the bandwidth can be if you're given n nodes? It could be 1, 2, 3, 4, 5, 6. It could be 5, right? It could be n minus 1. So this problem in a very, very dense graph where the bandwidth comes almost close to the maximum could end up being as bad as n to the n minus 1. So it is not a polynomial time algorithm, but it is a polynomial time algorithm if you fix the bandwidth that you're interested in. Now it's possible that even something like this wouldn't exist. It's possible that even asking whether the bandwidth was 2 could have been an NP-complete problem. But the answer is it's not. You can do it for a fixed k. So it's a pseudo polynomial time algorithm. Let me back up for a second. If somebody gives you a graph and asks for the minimum number of colors to color the graph, remember coloring? Just color this with different crayons and make sure that no two things that are connected have the same color. So B and E have to have different colors. E and D have to have different colors. And you want to know what's the minimum number of colors I need. That problem's NP complete. If I ask you, does a given graph need 3 colors or does it need more? Does it need 3 colors or less? Yes or no? That problem is also NP complete. That's a harder problem than bandwidth minimization in the sense that I could fix the number of colors I'm interested in and I still don't have a good algorithm. Everyone understand that distinction? Let me say it again. If I give you a graph, a big complicated graph, and I say, does this need 3 colors? Does this need more than 3 colors, or can it be done with 3 colors or less? That question for a general graph is NP complete, even though we fixed it on 3. This problem we can handle if we fix the size of the minimization that we're looking for. The minimum coloring problem we can't handle even when we fix the size. There's a really cool approximation algorithm for this, but there's no absolute algorithm to figure out the answer. So that's a harder problem. This is at least workable. Questions about this? Yeah. You have a question? No? Other questions? All right. I don't want to go into the details because I'm not sure how useful it'll be. I did write them up in the notes and you can look at them. But briefly, just to give you some bare intuition, just a 5-minute little thing, this uses dynamic programming. And what it does is instead of looking at all the different ways to lay out the values, there's a lot of ways. How many different ways can you lay these things out? There's n things, and you want them in a particular order. So it could be n factorial. It's a lot. You don't want to try all n factorial possibilities. But if we only care about bandwidth 2, then here's what we end up doing. We start laying things out. Say we start with A, and then we go to F. And now we go to E. Now at this point, we can erase A. How come? Because if we're looking for bandwidth 2, there's no way for A to have any edges that are ever going to contribute to anything interesting later on. A is already 3 away from my next node. So I erase it. And I leave those hanging off the end. The point of the algorithm is you never need to actually store more than 2 nodes at a time. They represent kind of where you are in the middle. And how many different possible ways are there to store 2 nodes at a time? There's only n squared. And that's the hook on this algorithm. Instead of looking at all the n factorial possibilities, you look at all the n squared little partial middle layouts. And you see if they can be extended. And they get extended to new partial layouts. F and E, they connect to B and to D. So let's see if we can lay B out. Here's B. Here's D. Now I get rid of these 2. I know I've succeeded so far. So all I have to know is see if I can succeed from BD. I only keep track of 2 nodes at a time. And I start up with nodes on a queue that start at the beginning. And every time they can be extended, I throw those pairs of nodes back on the queue. And I keep going forward and forward and forward. And if I ever end up with a pair of nodes that have no edges coming out of them, then I'm all done. Yeah?
That seems really different from the dynamic programming we've done.
It's very different. It's different in the sense that what we've done is we always identify all the subproblems and list them out and methodically go through each and every one. Here, we don't really know the subproblems that are going to come up. Some of these pairs will never show up. So instead, we start with an arbitrary pair, and whichever ones that it generates, we throw in a queue. It's a lot like memoizing.
It seems almost like it's got some similarities to greedy programming within the... I mean, not overall.
It does in some ways, but we're trying all the possible ways of extending BD. We actually don't pick the best one. So it doesn't have that aspect of greedy. We really do try everything, and the total number that we might try is only n squared. I spent 3 minutes discussing something that I think really takes at least an hour or 2 to get any real inkling of. So don't concentrate too hard on it. I'll be happy to spend other times, maybe recitation, talking about it. But let it go. Just keep in mind that there's a cool way. It has to do with the fact that we focus on the number of different partial layouts because we don't have to care about the stuff earlier. It's a neat idea. It needs at least a half a lecture to really get through. But take it for what it's worth, just as an example of a cool problem that's pseudo polynomial time that you can handle in some way. Yeah, Joe?
No.
Yeah.
Can you recover the path there?
Can you recover the layout?
Yeah. You have to run through it again.
Yes, you can recover the layout. You have to store things along the way as you go, but it's a little tricky, yeah. By the way, that reminds me, in the knapsack problem, we did not keep any information about how to recover the actual objects. But how would we keep such information? When I wrote down a particular number like 5, that 5 came from a choice. Either the first one was the biggest or the second one was the biggest. All I have to do is remember which one gave me the biggest. I'll put first or second in every little box. And as I work my way back, if it's first, I go back to the first recursion. If it's second, I go back to the second recursion. Either I go up or I go to the left. And if it's first, I go up, and if it's second, I go to the left. And that way I work my way back up, looking to see what happens at each stage. So I could easily store the first or second values. Here, it's a little trickier to do it, but you can still do it. Okay. I don't know. I mean, this is really cool. It's worth talking about, but we've done a lot of dynamic programming. I think it's time to let it go and move on to greedy. So I'll take about 10 more minutes, then I'll quit today to talk a little bit about greedy algorithms. We'll continue with greedy stuff tomorrow, finish up with it tomorrow probably. I'm not going to spend as much time on the greedy algorithms because 2 reasons. Greedy algorithms tend to be easy to describe. They're greedy. You just do the most obvious thing first. They're usually not these like clever recursive schemes. The proofs why they work are sometimes very deep and clever. But they tend to be easy to describe. What's more is that there is a nice mathematical theory behind greedy algorithms, which is a little deep and a little much for a first course. It's called matroid theory. It does give us this cool way of playing that game I mentioned, this game that called Bridget many years ago in the United States, or the Shannon switching game in a paper. It does some really cool stuff, matroid theory, but it does not encompass all of the greedy algorithms. It encompasses a lot of them, but not all of them. So one of the most famous greedy algorithms that we will talk about tomorrow is called Huffman encoding. And the matroid theory does not encompass Huffman encoding. Huffman encoding needs a more general theory to find its place as a special case. It just sits there as just another example of something that happens to work with greed. Huffman encoding is really cool because it lets you take your files in binary and compress them down and send them over, and sometimes you can save 50%, sometimes even 90% of the size, just by encoding it in a more efficient way. A greedy algorithm ends up being a good approximation algorithm. So it's always good to consider greedy algorithms, but in order to really do them, anybody can think of them, and not everybody can prove that they work. And not everybody can always find one that actually does work. So the proof is really the difficult part of it. Let me give you one quick example of a greedy algorithm. It's the warm-up one in the book. It's a very nice one, and it's kind of straightforward, but it's a good one to finish off with today before we go into more complicated ones next time. All right, the example I'm going to do is right from the book, so you don't have to copy it. I'll give you the page. It's 331. And the book calls this activity selection. Let me give you an idea of what it is. Somebody gives you a list of activities as far as how long they're going to take. Like there's going to be a talk this afternoon from 1 to 3. There's going to be a party from 2 to 6. There's going to be a lecture from 9 to 10. Okay, and they give you all these lists of times for these activities. The example in the book gives you this particular list. 1 to 4, 3 to 5, 0 to 6, 5 to 7, 3, 8. Don't copy this. It's right in the book. You can look it up. 6, 10, 8, 11, 8, 12, 2, 13, and 12, 14. Different time periods at which activities are going to occur. You're supposed to figure out the maximum number of activities that can run in this complete time frame. They can't overlap. You only got one place to run these activities. So somebody gives you this list, and you want to see how much you can squeeze into a day. Everyone understand the problem? So what's a brute force way to do it if you were given n different activities? A brute force way is to take every possible subset of these and see whether they overlap. I could try this one, and this one. But they overlap. 1 to 4 and 3 to 5 overlap, so I throw that away. The number of subsets of n things is 2 to the n. So that's a horrible way. So let's try a greedy strategy. Let's say we were in day camp. In day camp, the counselors are very good with the kids, but none of them sit and study algorithms all day long because the kids would run and hurt themselves in the pool. So I used to work in a camp. So how do you do it? Just do the greedy thing. Say, okay, well, we know we have something to schedule 1 to 4. Let's schedule that. Now it's real easy. Now we've constrained ourselves down. It's easier to pick the next one. We can't pick 3 to 5, right? No good. We can't pick 0 to 6. What's the next one we can pick? 5 to 7. So we'll run that one. Can't do 3 to 8. Can't do 5 to 9. Can't do 6 to 10. We can do 8 to 11. Can't do 8 to 12. Can't do 2 to 13. We can do 12 to 14. So this is our orientation day. Every camp counselor gives in a bunch of different activities they want to do. You put them on a list. You go through this little method, and you come up with the best number of things we can do during the day. Do this 1 to 4, do this 5 to 7, do this 8 to 11, do this 12 to 14, 4 different items.
It seems, I mean, if you had one activity that goes from 1 to 7, but you had then further down the list an activity from 1 to 2, 2 to 3, 3 to 4, 4 to 5, you could easily make more things available to happen if you didn't do the 1 to 7 thing.
Yes. Something like this, you mean? Mm-hmm. Right? If we did this, and we checked this one, then we'd say this can't be done, this can't be done, this can't be done, so that's the best we can do. Or what do you think?
The first one with the shortest time period.
Order them by shortest time period? Okay. Okay, another idea.
Could we topologically sort this?
First, let's check. Is Chris' counterexample definitely true? If you start with this method and just go through that this gives you 1 activity, but this gives you 4 activities. So before we come up with all these different methods, and we don't go down like a wrong, misleading trap, this is considered just as good as these, because it's
Whole day's worth of activity.
right. Right. You care about scheduling time. I said maximum number of activities, but I meant maximum number of time slots taken up. So here you're still busy 1 to 7, and if you did all these, you wouldn't be busy for more hours. You just I don't.
No, you skip the 6 to 7.
8 o'clock as opposed to going to 7.
But you skip the 7. You skip the 6 to 7 hours.
Right, but you only get 1, 2, 3, 4 altogether of hours, and here you get 6 hours altogether.
Well, have an activity that runs from 6 to 18, then.
How about? Well, I can't use 6. I got to use.
But the book lets you have 6. So
How about 5 to 18?
At the end of one overlap with the beginning of the next, can't
No, it's like closed intervals.
I think the book uses a paren and a square bracket notation. They let something start.
They let something start and end? Okay.
At that single moment.
Okay. But this is an okay counterexample too, right? We'd start here at 1, 7. We wouldn't be able to do anything else. But we could definitely do all these. What do you think now?
Might be useful to topologically sort it based on things that come earlier in the time can precede the others.
You don't mean you mean lexicographically sorted by this first.
Topologically,
When
meaning that something, in order for something to, make a graph out of it, in order for something to point to the 3-5 node, it has to end before 3.
Okay, I understand. Good idea, maybe. I got to end in 90 seconds, so I can't follow this idea through, and I'm not going to be able to finish this, but I'll continue it next time. Just think of this as completely open-ended right now. Before I leave, I want to give you another example of a problem that's like this, and it's an example that relates to one little problem you had in a problem set before. I once told you about interval graphs in a problem. And a lot of people say, why don't you just write the graph down? And the reason is that interval graphs are an unusual kind of graph that you don't hear about much when you're first starting. You'll hear about trees, you hear about acyclic graphs, then you hear about this weird interval graph. So here's a problem very similar to this, and it's one of the problems in the problem set in your book, not in the problem set that I gave you, but it's a cool problem, very similar to this one. And imagine somebody gave you a bunch of time slots just like this, that represent particular classes in a school, and they want to find out the minimum number of classrooms to handle all these classrooms. Okay? So you have to do all the classes. They have to be done. You can't just leave some out. So for example, in this case, we could use the same class for all these checked objects. We'd have to come up with another classroom for the rest of them. Everybody get the idea? That problem is easily representable in a graph. Every one of these becomes a node in a graph. We're going to make an edge between two things if they overlap. So there's no edge between here and here because they don't overlap. But there's going to be an edge between here and here and here and here. And there's going to be an edge between here and here, and there's other edges in the graph. That's what an interval graph was, right? We make an edge between two nodes if they represent intervals that overlap. So here's a graph that represents these numbers now. And what we want to know is, what's the smallest amount of colors to color this graph? Every color represents a lecture room. So if I use red, the red room, to have this lecture, then I cannot use the red room for these two lectures. I need to use a different room. I can use the red room for this one because it doesn't connect to that R. So this one will be colored R also. Everyone understand how this lecture scheduling problem turns into a graph coloring problem? The lectures become graphs and nodes and edges. Overlapping time slots become connected edges in my graph. And if you color them with the two same colors, that's a room clash. So you want to know what's the smallest number of rooms to use to schedule these. That's the smallest number of colors to schedule this, to color this graph. So it's a minimum coloring problem on an interval graph. Is minimum coloring NP complete for interval graphs? I don't know. Got to look it up. Is there a good approximation algorithm for this? A good greedy algorithm? There's no approximation algorithm except the general one for coloring, but there is a good greedy algorithm. So the answer is that coloring is possible to be done with a greedy algorithm for very special kind of graphs called interval graphs, even though I told you coloring was very hard before in general. For interval graphs, you can do it. And the greedy algorithm for this is similar to the greedy algorithm for this. And we'll flush at least this one out in detail next time, and then we'll move on to Huffman encoding. Okay? Let's quit.